Welcome to homework.
All right, so this problem is more mathematically motivated than many other problems, but it is a cosmology problem focusing on the density parameter. And here you have a pressureless dust as the only component. Pressureless dust is the only component in this hypothetical universe. And so you start out with this equation, 1 over r dr dt. Actually, you start out with dr dt, 1 over r times dr dt squared, minus 8 pi g over 3 rho density. That whole thing is squared. That whole thing is, multiplied by r squared. That's equal to minus kc squared, curvature times speed of light squared. The r's cancel out and you get dr dt squared minus 8 pi g over 3 times rho t times r squared, and that is equal to minus kc squared. Then what you can do, now we're focusing on this term in the middle, you can multiply 8 pi g over 3. You can multiply and divide by rho c, the critical density. And so that's what that is. And what you get then is 8 pi g over 3 times omega, which is what you want, times the definition of critical density, which is 3h squared, h being a time-dependent Hubble parameter, not the present-day Hubble constant, over 8 pi g times r squared. And so a lot of things cancel, as you can see. You're left with omega times h squared times r squared. And we know that h squared times r squared has an interesting form from equation 24 in the book, equation 24. And so this becomes omega times kc squared over omega minus 1. So that's what h squared r squared becomes from equation 24. And so therefore, we go back to our main equation here, dr dt squared minus omega times kc squared over omega minus 1 is equal to minus kc squared. All right, and then you take kc squared as your common term, and so you go kc squared times omega over omega minus 1 minus 1 is equal to dr dt quantity squared. So down here you have omega minus 1. So these omegas cancel out over omega minus 1. So the right hand side becomes kc squared times 1 over omega minus 1. And so omega minus 1 is equal to kc squared over dr dt squared. And you add 1 on both sides, you get omega equals 1 plus kc squared over dr dt quantity squared. And that's your part A. So that was part A. All right. And so what this says about the early universe is, omega has to be a positive number. It's rho over rho c, and so the left-hand side is positive. Right-hand side must also be positive, and so k cannot be less than 0. So early universe, you have k greater than or equal to 0. It cannot be negative, because if it's negative, then the right-hand side won't be positive as the left-hand side is. Okay. And for part B, you note that omega of t will go to 1 at early times as t goes to 0. Early times, density over critical density is roughly equal, and so t goes to 0, omega goes to 1. Therefore, the right-hand side has to go to 1 as the left-hand side. And for that to occur, you need this denominator. Therefore, let's see, 1 plus kc squared over dr dt quantity squared has to go to 1, which of course means that this term will have to go to 0. And the only way for that to happen is the denominator has to go to infinity. Denominator has to be really large so that the right-hand side becomes 0, becomes 1 as this term becomes 0. So this means, of course, that at early times, this universe was, at least flat and at least flat or open. It cannot have been closed, and whatever was the case in early times, that curvature carried on to later times, and that's it.